We're looking for all ordered pair solutions to this integer equation. Another way of putting this is just m, the ordered pair mn, where this is a member of the Cartesian product z cross z. And of course, z is just the positive integers combined with the negative integers along with 0. Okay. Now, this is equivalent down here, but just in case, we're looking for ordered pair solutions. Now, notice this is one equation, two unknowns. Okay, one equation, two unknowns. And so normally you can have an infinite number of solutions to something like that. You can have none, you can have one, I guess. But what I've done is rewritten it in an equivalent way where I factored an m out. Now, we probably could have done the same thing by factoring an n out. So we get to this point right here where part of it's factored, but then you have these two unfactored terms to the right. Now, this common binomial factor is a really cool idea. It even has a name, I think. But notice that if you add, take 5n plus 8, all right, and you add, if you add 8n to it, minus 32, and this is just kind of an inspection thing, you get this value right here. 8n plus, 8n plus 5n is the 13n that you see right here. And of course, plus 8 minus 32 is negative 24. Now you see I highlighted this. You get a common binomial factor, and we've turned this into a factorable circumstance. Now, let's, again, I like showing this. I do this every time to everybody's irritation, I'm sure. But if you put this parenthetically, there's an understood 1 right there. Okay, and I'll keep doing that because it seems to be a super common error when people are getting used to algebra. So that's where that 1 comes from. Now the cool thing about it is now we have it, both sides are factored, and you can make some progress by considering this expression modulo 8. It simplifies to something very nice. Now notice the right-hand side is a multiple of 8, all right? So in other words, you can rewrite it this way. Now, I put the y here. Well, notice that 13 is congruent to 5, mod 8. Modulo 8, I'll leave that out. And this 13 got replaced with a 5 down here. Now, look, 24 is congruent to 0, right? 24 is congruent to 0. All right, that's why the 24 went away, all right? And then that explains, and also, folks, of course, 8 is congruent to 0 also, right? So that's why the right-hand, this whole right-hand side, let me just write that. 8 is congruent to 0. Okay, so that explains how this object right here, which was an equality, became this congruence, okay? So now let's move along. Now y'all, right off the bat, you can see that m equals negative 1 is going to be one of the solutions. I'll say, yeah, m is equal to negative 1. Okay, if you put a minus 1 right here, you get 0 on the right-hand side, and anything divides 0, right? Also, you would, m equals 7 would give you another possibility, right? I'm just picking numbers kind of close, relatively small numbers. 7 plus 1 is 8, right? So this whole thing would be divisible by 8. And then also, what else could we pick? We could pick, you could try out a negative 9. Right? Why is that, folks? Because when you put minus 9 right here, you get negative 8, which is, of course, divisible by 8, right? So these are some tries to substitute back into the original equation. Okay, and that's what I did. This is our original equation. This is the problem equation right here. Okay, and when you substitute m equals negative 1 in right here, you get this statement. And let's see, does that end up being minus 8n equals to 32, right? Or minus, yeah, and you take that to the other side, so you get minus 8n equals to minus 32. Okay, and so what we know, we have one solution. That solution would be minus 1 and 4. Okay. So this is one solution. Let me get that circled. And you see it's kind of nice how this congruence gave us some ideas on the type of m's to select. And then once we figure out an m, we can solve for n. Okay. Now right down here, similar, if you substitute this choice 7n, you get this, and I didn't finish this one either, but this would be what, 96n? 96n, and we are looking for integer solutions, right, folks? 96n, and this would be minus 160 on this side, so that would be 160 over here, right? 160 right here. But notice that n is not an integer. Let me write this down. I won't even. There's no need to say much more than this. N is not a member of the integers, right? It's a fraction. It's 160 over 96. So it's not a member of z, so we can't use that, right? It's a solution, but it would be a fractional solution, namely 160 over 96. Okay, now let's try this try right here, minus 9. When you do minus 9 in here, this becomes, what's happening here, you would have minus 112n. Okay, 216 and 8 is 224. You take it to the other side, and you get minus 224. Okay, and that tells you that n is equal to 2. N equal to 2. And so, folks, right here, another solution would be minus 9, comma 2. Okay, so we have 2 solutions so far. Now, I tried a few others. Then it occurred to me to try this idea down here. You can actually solve for n, which is what I did right here. And I want to make an observation here that helps you out quite a bit. This is kind of a calculus concept, but we can use it discretely. Notice that as m becomes unbounded, as m approaches plus or minus infinity is the way they were that in calculus, but you can just think of it as m is getting larger and larger and larger in the positive or the negative direction. That implies that n itself, let me just write this out, implies that n is approaching. Now again, you can reason through this. You don't even need to think calculus here. What happens here, these constants get wiped out as m gets larger and larger and larger, or smaller and smaller and smaller. It's still going to cancel out. And so this is going to approach 24 over 13, right? Now notice that this number is not even 2. It's less than 2, right? It's between 1 and 2, in fact, right? But you see that when you're close in, when you're using these smaller values of m, you're not that close to 24 over 13 necessarily. That explains how we could get a minus 9 and a minus 1, right? Because you haven't moved that far out from the origin. But the further away you get, the more that means that n is going to get closer and closer to this number 24 over 13. This would be what they call a horizontal asymptote. Horizontal asymptote, if you were to graph this, But anyway, for that reason, there's no more solutions, because you eventually, there's only so many integers to go around in these regions, right? And what I've done is, so these are the only 2 solutions. Now I know that's not a completely rigorous sort of thing, but notice we got minus 1 and 4. Now what I did is I was going to hand sketch it, and I decided, well, I'll just go ahead and get the computer to graph it. But notice that these are scales of 4. Okay, so this point right here, and again, it might take some convincing, but that point right there would be minus 1, 4. And again, what you need to do is think of the horizontal axis is the m axis, right? Okay, the m axis, and the vertical axis as the n axis instead of the conventional x and y's you're used to. So remember that minus 1, 4 is that point up at the top, and then minus 9, 2 would happen out here. But what, and y'all, these are increments of 8. So minus 9, 2 would be approximately right there, right? Now you're saying, well, that doesn't, you're right, that doesn't prove squat. But what it does prove is the further you move to the left and right, which you can intuit just by writing down the limit statements, that's minus 9, 2, again, which was, let's run back up here, these solutions, minus 1, 4 and minus 9, 2 are represented on the graph thusly. Okay, both of them are on this side. Both of them have negative coordinates. But you can see how you don't have to try many other numbers. You could try minus 17, but this is an increasing function. You could try minus 17 would be congruent, minus 25. But you can see that there's no way that's going to be an integer, all right, because it just gets close. It's never, it's based on this idea of a limit in n becoming smaller and smaller and smaller. It's always less than 2, I guess is what I'm trying to say. It's always less than 2. So it doesn't get below this horizontal asymptote, okay? Now again, not a rigorous proof, but hopefully it convinces you that these are the only 2 solutions. You could do some inequality analysis, I guess, and make it conclusive. But I thought it was kind of a nice connection between rational functions. Notice that this denominator, if this is equal to 0, you get what the vertical asymptote. You guys are probably familiar with that. M would be equal to minus 5 over 13, right? And remember, the vertical asymptotes are the point on the graph where the function is not defined, because you'd be dividing by 0. And if you take a look right here, we do have a vertical asymptote right along in here that's not quite coincident with the n-axis, right? So everything jives. You can also check that minus 8/5 would be about right here somewhere. Okay, or let's see, yeah, this is 2, so minus 8/5 would be the y-intercept. But in any event, let me know what you thought. I think it's okay to use the graph. I wouldn't call this conclusive that these are the only 2 solutions. I haven't done a complete, rigorous demonstration, but hopefully these limit statements convince you that these are the only 2 solutions. Thank you for viewing.